Myself, Dr. C.R. Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the down and up conversion luminescence behavior of Thulium-3 plus and Yttrium-3 plus co-doped tellurite glasses. This is one of the important topic from the laser glass spectroscopy. So outline of the today talk is on the introduction, experimental methods or techniques, results and discussion of the down conversion and up conversion luminescence behavior of Thulium-3 plus and Yttrium-3 plus co-doped tellurite glasses. Finally, conclusion or summary of the Thulium and Yttrium co-doped tellurite glasses. So, these are the contents going to study in the present topic on the down and up conversion luminescence behavior of Thulium-3 plus and Yttrium-3 plus co-doped tellurite glasses. So, what are the importance of lanthanum-3 plus or rare earth ions? So, among the lanthanum ions, from lanthanum to lutetium, 14 lanthanide elements. Now, among the 14 elements, we are going to study the thulium and yttrium, how energy transfer takes place, what are the important applications in the thulium and yttrium co-doped tellurite based glasses. So, electronic configuration of rare earth elements is incomplete inner 4FN orbital configuration. So, xenon 4FN2, 5s2, 5p6, that is the electronic configuration of the rare earth elements. What are the optical properties of the rare earth elements is strong absorption and fluorescence, wide range of excitation levels and emission in the range of ultraviolet, visible, infrared regions. These are the optical properties. What are the important applications? Rare earth doped laser glasses. These laser applications, displays, sensors, lighting and biomedical imaging, etc. These are the important applications involved in the rare earth doped laser glasses. This image shows the blue emission to, that is visible to NIR region, that is a thulium, terbium, dysprosium, europium, samarium. These are exhibit the visible region emissions, and the yttrium, Nd and erbium, these are exhibit the near infrared region emissions. So this figure shows the what kind of rare earth elements exhibit the visible emissions, which rare earth elements exhibit the near infrared emission. So this particularly yttrium, neodymium, erbium is exhibit the high power laser applications we can use in the case of near infrared region. Particularly these elements, it exhibit the near infrared emissions, and the visible emissions also thulium, terbium, dysprosium, europium, samarium, they exhibit in the visible regions. So these are the importance of lanthanide ions or rare earth elements. So rare earth elements. So 4FN and 5 black elements and their unique to trivalent state, 4FN electronic shielded by the 5s2 and 5p6 electron configuration, and so many advantages involved in the rare earth elements. Glasses. Glass is an indispensable photonic platform material due to its high optical transparency, thermomechanical strength, and ability to be shaped into almost unlimited range to geometrical structure and composition. So, we can vary the different kind of structures from bulk to fiber, and different kind of composition also we can vary. We can prepare the different rare earth doped laser glasses. What are the applications? So, laser gain media, fiber amplifiers, optical components, medical accessories, different kind of medical applications we can use, and massive structures we can study by different kind of massive structure applications also, by you can use study the different rare earth doped laser glasses, and entertainment also we can study. These are the different applications of different variety of rare earth doped laser glasses. Just rare earth ions in glasses. So many applications, particularly mainly very important application is laser gain media and optical fiber amplifiers. That is particularly telecommunication and optical communication applications. They are using for the different kind of rare earth doped laser glasses. These are the this is the main introduction involved in the particularly in the thulium-3 plus and yttrium-3 plus co-doped tellurite glasses. So visible lasers are essential tool in all walks of life, notably in display, optical recording, medical diagnostic, and underwater directions. They are using for the different kind of rare earth elements doped with the glasses. Just among the various methods available for generating the visible lasers, tapping and energy up conversion and down conversion phenomena in the rare earth elements under infrared and ultraviolet pumping is an effective method. So we can pumping with near infrared and ultraviolet and visible emission. These are we can pumping with. We can study the different kind of down conversion emission or up conversion. These are used for the energy up converters and down converters also we can use for the different kind of rare earth doped laser gas. So particularly rare earth based luminescent material have increased much research attention due to their excellent luminescence behavior for optical gain. To understanding the energy transfer mechanism and efficiency of the system can provide an important platform for tapping of benefits of efficient rare earth elements active luminescence materials. Just among the various rare earth ions doped laser systems, thulium, that is the thulium 3 plus doped glasses exhibit excellent luminescence properties, in particularly 1.2 micrometer emission associated with 1G4 to 3H4 transition in advantage for optical fiber amplifiers they are using for the mainly thulium 3 plus doped laser glasses. On the other hand, ytterbium 3 plus, that is Yb3 plus, is typically used as a sensitizer in rare earth elements doped with luminescence materials because of its simple energy level scheme, large absorption and emission correction, and a longer lifetime excited state of WTF 5 by 2. So excited state of ytterbium ions, it exhibit the larger absorption and larger emission cross section, at the same time longer lifetime of the ytterbium 3 plus. These are the important introduction about the ytterbium and thulium 3 plus doped laser glasses. Next, material selection. So in our present study, we study the down and up conversion luminescence behavior and energy transfer analysis in thulium 3 plus and singly doped thulium 3 plus and co-doped thulium 3 plus and ytterbium 3 plus co-doped tellurite glasses. So here host material is tellurite because we are taking the 50 mole percent of tellurium oxide and 30 mole percent of zinc oxide and 10 mole percent of yttrium fluoride and 10 mole percent of sodium fluoride and 0.5 mole percent of thulium oxide. And why we are varying, that is X is 0.5, that is fixing. Y is we are varying the concentration 0.5, 1 mole and 3 mole of the ytterbium 3 plus ion concentration. So singly doped and co-doped tellurite glasses we are going to study in the present study. So preparation of laser glasses. So preparation glasses is conventionally melt quenching technique we are preparing. First we have to take the weight of the chemicals in batch composition of 20 grams. Here put into the agate mortar. We can find the powder chemicals. After find the powder by using thoroughly grained fine powder, then it put into the platinum crucible. After platinum crucible, we are covered with the lid. Then we are put into the electrical furnace at the temperature of 1450 degrees centigrade for 2 hours. After taken to the pour into the preheated brass mold. After melting the, we can keep into the annealing temperature at 400 degrees centigrade for 2 hours. After cool down to the room temperature, we can take into the glass sample. We cut pieces for different kind of small pieces and we can study for the different spectroscopic properties of the prepared laser glasses. So this is the preparation technique for the laser glasses. Is mainly we are using method is conventional melt quenching technique. Next, what is the experimental technique methods characterization? So here absorption spectra we are using for the Perkin-Elmer spectrometer, wavelength range from 250 to 2500 nanometer. And the fluorescence and decay time measurements we are using for the fluorescence and the lifetime measurements we carried out by using the Jobin YN fluorolog 3 spectropolarimeter, and all the measurements were carried out by using at room temperature only. These are the experimental technique or methods of the present study. Next, first discussion we are going to discuss the absorption spectra. So this is the optical absorption spectra of thulium 3 plus and yttrium 3 plus co-doped tellurite glasses. In this we are observing from wavelength versus absorption. So 400 nanometer to 1400 nanometer we have studied by using absorption spectra. So the thulium 3 plus ground state is 3H6. So you can exhibit the ground state 3H6 to different kind of excited states. So the thulium and yttrium co-doped glass sample absorption spectra shown in figure. The well-resolved absorption peaks at 465, 683, 790, 1210 nanometer correspond to the energy transition of the thulium from ground state 3H6 to different excited state of the 1G4 and 3F2, 3F3 and 3H4 and 3H5 excited state levels are observed in the peak at 1220 nanometer. This particularly this peak. mainly belongs to the, that is 978 nanometer here. This mainly belongs to the yttrium 3 plus. That is, these are the mainly due to the thulium 3 plus energy transitions. Particularly in the case of 1210 nanometer is mainly belongs to the yttrium 3 plus because we are using co-doped laser glasses. That means thulium and yttrium. So the among the 1, 2, 3, 4 transitions mainly belongs to thulium 3 plus ions. Only one transition is mainly belongs to the yttrium 3 plus ions. That is 2f7/2 to 2f5/2. This is important transition, particularly in the 978 nanometer, that corresponds to the transition from the ground state 2f7/2 to the exit state 2f5/2. That is mainly due to the yttrium 3 plus ions. Remaining are the transitions that belongs to thulium 3 plus ions. This is the absorption spectra of the thulium 3 plus and yttrium 3 plus co-doped tellurite glasses. This is the excitation spectra of thulium 3 plus and yttrium 3 plus co-doped tellurite glasses. This is the excitation spectra. See the your emission, we are monitoring the 1020 nanometer, and we are getting the three important emissions. One is 3h62 1g4 and 3h62 3f3 and 3h62 2h6. These are the important emission transitions from the thulium 3 plus ions. This excitation spectra of tellurite glasses recorded at room temperature under the emission wavelength of 980 nanometer, and monitoring the emission is 1020 nanometer. We are getting the different kind of excitation peaks. The rise in intensity could be attributed to energy transfer from the thulium 3 plus ions to yttrium 3 plus ions. See, the intensity is increasing. This is the mainly source to the rise in intensity could be attributed to energy transfer from thulium ions to yttrium 3 plus ions. So these are, we are going to discuss more details in the above. Next, down, this is the emission spectra, that is down luminescence spectra of the thulium 3 plus and yttrium 3 plus co-doped tellurite glasses. See here, we are exciting emission is 467 nanometer. That is, your pumping energy is high. So this is down conversion. Down conversion means input energy is more and output energy will be very less. In the same, we are studying here the excitation of the wavelength. Pumping energy is 467 nanometer. We are getting the around 650 nanometer. This one is from the 650 nanometer, other one is 790 nanometer. These are the two emissions we are getting from the thulium 3 plus to yttrium 3 plus ions. The energy transfer from thulium ion to yttrium 3 plus ions might be the cause of the decrease in intensity for the transition 1g4 to 3f4. This is 1g4 to 3f4. However, there has been a slight increase in intensity might be attributed to the following cross relaxation energy transfer process involved in the CR1. CR means cross relaxation process from CR1 to CR2. The energy transfer takes place, so that is mainly due to the cross relaxation process. That cross relaxation channels we are going to study in the energy level diagram. Next, this is the upconversion emission spectra. So upconversion emission spectra of the thulium 3 plus singly doped and co-doped thulium and yttrium co-doped tellurite based laser glasses. We are pumping with laser excitation is 980 nanometer. We are observing the upconversion emissions in the case of thulium and yttrium ions. So 3f1 to 3h6 and 3h4 to 3h6. These are the important two upconversion emissions we are observing the by pumping with 980 nanometer. We are observing the two important upconversion emissions. That is, from one is 600 to 850 nanometer we are observed. One is 690 nanometer emission we are observing, and other one is 800 nanometer was we are observing. This is upconversion emissions. It is noticed that with increasing of yttrium 3 plus ions concentration, the intensity of two emission transitions has been increased. So this emission and this emission, increasing the concentration, it will allow almost the 0.5, 1 mole, 3 mole. So 3 mole percentage of thulium and yttrium almost increase here. Upconversion is increased double. See here, low intensity. While increasing the concentration of 3 mole concentration, almost the intensity of upconversion luminescence intensity will be increased to more than 5 times or 10 times. So this is, notice that with increasing of yttrium ion concentration, the intensity of two emission transitions, particularly in the 690 nanometer and 800 nanometer, to progressively increasing of energy transfer from yttrium 3 plus to thulium 3 plus. That is mainly observing the energy transfer takes place from thulium to yttrium. That is why luminescence intensity will be enhancing from 10 times or more than 20 times also. We are observing by studying the thulium and yttrium 3 plus co-doped tellurite laser glasses. Next, lifetime measurements. We are studying the lifetime measurements. This is decay time or lifetime measurement. 3H level of thulium-3 plus ions, particularly thulium-3 plus and thulium-3 plus and yttrium-3 plus co-doped Tellurite glasses. This is a lifetime measurements from we are observing this visible emission. That is, we are exciting 467 nanometer and emission is nearly 800 nanometer. That is, we are focusing this emission channel. That emission, excited state emission, we are focusing here. We are studying the 800 nanometer emission, pumping with or exciting of 467 nanometer. We are observing the lifetime increasing the concentration. So, thulium, that means singly doped one. That means zero concentration of yttrium is, that is completely thulium one. That is, we are getting 156 microseconds. While increasing the yttrium concentration from 0.5 to 3 mole percent, the lifetime will be increasing 141, 124, next 100. That means lifetime is decreasing. That is mainly due to the energy transfer takes place from thulium-3 plus to yttrium-3 plus ions. That is a lifetime also decreasing from 141 microsecond to 104 microsecond. That is clearly shows the energy transfer takes place from thulium-3 plus ions to yttrium-3 plus ions. This, although all gases have the same concentration of thulium-3 plus ions, the decrease in lifetime of thulium-3 plus 3H4 level is mainly because of energy transfer takes place from thulium-3 plus ion to yttrium-3 plus ion. That is why lifetime measurements also decreasing from 141 microsecond to 104 microseconds whenever increasing the concentration of yttrium ions in the case of thulium-3 plus ions. So this is the partial energy level diagram of thulium-3 plus and yttrium-3 plus ions co-doped Tellurite glasses under excitation wavelength of 467 nanometer, particularly thulium-3 plus ions. This is the partial energy level diagram of thulium-3 plus to yttrium-3 plus. Yttrium-3 plus ions having only one emission channel, that is the around 1000 nanometer. That is the ground state 2F7 by 2, 2F5 by 2. These are the thulium energy level diagram. This is the cross reaction CR1. This is different energy transfer takes place particularly in thulium to yttrium. For the transition from 1G4 to 3F level, however, there has been a slight increase in intensity might be attributed to the following cross reaction channels. That is followed by any one cross reaction takes place in the case of thulium-3 plus to yttrium-3 plus cross reaction channel CR1. That is mainly due to the this transition to this transition energy transfer takes place. That means this transition bandwidth will be similar. That is why energy transfer takes place from this level to this level. If considering CR2, say energy transition from 1G4 plus 3H6 to 3H5 to 3H6. These two channels and these two channels energy will be almost similar. That is why cross reaction takes place from this level to this level. Next CR3 from 1G4 to 3H6. From this level to this level, maybe energy transfer takes place. Same in CR4 also 1G4 to 3H6 to 3F3 to 3F4. Energy transfer takes place from thulium-3 plus to yttrium-3 plus. That means this energy level and here energy levels will be both almost matches, well resolved. That means this energy level bandwidth, this energy bandwidth is almost similar. Automatically energy transfer takes place from thulium to yttrium-3 plus ions. That is, we are discussing different kind of cross reaction channels is attributed in the CR1, CR2, CR3, CR4. These are mainly due to the energy transfer takes place from thulium-3 plus to yttrium-3 plus, and that is why lifetime measurements or luminescence intensity will be decreasing from lower intensity to higher intensity. That is, we are observing here lifetime also. See, increasing the concentration of yttrium ions, lifetime will be decreasing from 141 to 104 microseconds. That is mainly due to the energy transfer. That is energy transfer mainly involved in the any one of the cross reaction channels, CR1 or CR2, CR3. This is possible cross reaction channels in the case of thulium-3 plus to yttrium-3 plus ions. These are the partial energy diagram of thulium-3 plus to yttrium-3 plus co-doped Tellurite based glasses. Finally, conclusion or summary of the study of the down and up conversion luminescence behavior of thulium-3 plus and yttrium-3 plus co-doped Tellurite glasses. The Tellurite glasses with the fixed thulium-3 plus ion, that is fixed means here 0.5 mole percent of thulium ions, varying of yttrium-3 plus ion 0.5, 1 mole, 3 mole concentration were developed by melt punching technique and explored down conversion and up conversion and lifetime measurements were studied by the 3H4 level. In down conversion of 1.19 and 1.47 micrometer broad emission bands in near infrared region also we can observe in the present study. And the yttrium the concentration is not in the same. This is due to the cross reaction channel mainly involved in the CR channel, cross reaction channel 1G4 plus 3H6 to 3H4 plus 3H6 process. This has been confirmed further the decrement of lifetime measurements exerted state 3H4 level is 159 microsecond to 104. Sorry, this is 104 microseconds, decreasing from 159 to 104 microseconds. That is increasing the yttrium concentration automatically. Lifetime decreasing from 159 microsecond to 104 microseconds. That is the Tm3 plus yttrium core classes exhibit wide upconversion, that is UC. The upconversion takes place at the excitation of 980 nanometer, the laser diode. From these studies, the Tm3 plus and yttrium core classes could be potential candidates for spectral conversion and visible emission applications. It is useful for the Tm3 plus and yttrium-3 plus core Tellurite glasses. These are the summary or conclusions of the present study on down upconversion luminescence behavior of Tm3 plus and yttrium-3 plus core Tellurite glasses. So these are the references and citations are present in the present study. So this work is mainly published in the Inorganic Chemistry Communication in 2023. Last year, this paper is published. In this paper, we study the down conversion, up conversion luminescence behavior, as well as energy transfer parameter. Also, we have studied by using the thulium singly doped Tm3 plus and thulium and yttrium co-doped Tellurite glasses. These are the references cited in the present work. So, thank you. Next class, we will continue. Next class. Once again, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.